Uh, Hello, am I audible? Can someone confirm that I'm audible?
Yes.
Okay, thanks. We'll just wait for some more time. Let's see if others are joining the session. Okay, so is this the first class you're attending, or you have attended previous sessions, both of you?
I attended one, two sessions, but then I couldn't attend few of the classes because of some reason.
Okay, fine. What about Andrews?
This is my first session.
Okay, this is your first session. Okay, Sanjay, you are coming for every session, right? I remember your name. Okay, let me just share my screen. So for the people who have joined you, I am Chaitanya. I'm a doctoral candidate at IIT Madras, okay, from the Department of Chemical Engineering. So what are we going to do in today's session is we'll just summarize whatever professor have been discussing, and then we have few example problems where you are expected to solve those and give me answers, okay, using Aspen. Okay. So in case if you have any doubts while solving that particular question, you can just ask me. We'll discuss further regarding that. And in case if you have any other questions with respect to this lectures, we can discuss. Okay. So yes, let me just get started. So yeah, this is just summary of whatever I have discussed, and then so these are the few examples which Professor discussed: the separation of hydrocarbon mixture and then synthesis of acetaldehyde from methanol, and then later he had a case study, okay, on BTX separation through distillation, etc. So I have a few MCQs, okay, for you. Meanwhile, just keep your Aspen ready in case if you have. Before that, just let me ask you, how many of you have Aspen with you now? Uh, the six candidates are there in the class, right? Sachin, you have, okay. Sanjay, you have others? Do you have Aspena? Can we do an example problem? Yes, okay. Three of you have. Okay, fine. No issues. Since three of you have, we can just start right away. Okay, so before just going to Aspen, I have a few MCQs. Okay, this gives me a clarity that you're able to follow lectures and still you don't have any doubts regarding it. Just try to answer these questions. So in Aspen Plus, do we have a module for? Is there a unit operation which gives me simulation for memory separation? What do you say? Can we perform memory separation simulation using Aspen? Just put the answer in chat box, okay? So yeah, most of you are saying first. Yes, yes, you are correct, right? You know, while doing a memory separation process, what do? We just I'll show you this itself. Let me just take some example. So if we had to do any memory separation, what do? We just take an hypothetical case using the separator block available. We give the separation values. Okay, so it assumes that the separation can be done using some memory which is existing and gives us the net results. Right? So that's how the simulation of a membrane separation process is done in Aspen. Fine. So then later, so can you just tell me the order of their volatility using Aspen? You don't have to remember anything. If you have Aspen in front of you, just open it and do a simple property calculation and let me know the answer. Just check the boiling points. Okay. So we have a benzene, toluene, and xylene. Among these three components, which is the most volatile? Can you just place it in the order? People whoever have access to Aspen, can you just answer this question? So the three components you have are benzene, toluene, and xylene. You already know the answer, or you verified it now? Sachin, Sanjay, Patil, Nitish Kumar. Did you do a calculation now, or you already are aware of the answer? Okay, you already know. Okay, you studied it. Okay, fine. So and okay, for the people, so everyone know how do we check the boiling points in Aspen, right? Everyone over here. Yes, I'll just show you. So while searching component itself, straight away you can search. That's one way of doing it. When you go to specification component, just click on find. Let me type benzene. So let me just type on equal to. See, do you show this? BP in degree centigrade. So one way of getting it is just check the boiling point here itself. Another way is go to this analysis, or on the top itself you have pure component thing, right? So when you go to pure component analysis, you'll be able to find out. Okay, so just click on the analysis and then see at what is its saturation temperature at 1 bar or 1 atmospheric pressure. Okay, so that's how you'll be able to find the boiling point. Okay, fine. uh, Let me see. So as you say, it's benzene with 88, toluene with 119, and xylene with 147. Fine. So there is one more question. Fensky equation is used to calculate the minimum number of stages required using the DSTWU model in Aspen. Is it true or false? Others, can you respond? It's true, right? In while doing simulation, you'd have noticed that the distribution columns, the first two, has got some assumptions, okay? So which are based on Underwood, Fensky, etc. etc. So this will give you a simplified version of the design column design. However, the rad frac is the one which will give you the detailed design of the column. So the answer is true. Using Fensky equation, we calculate the number of minimum required stages for given separation. Okay, fine. So yes, which among the following methods are relevant base methods if the petrochemical method is used? Can you just open Aspen and check what all the equation of states or the property methods available under the petrochemicals? See, no one expects you to remember all this. Okay, just these questions are framed so that you'll know how to check Aspen. I mean, these questions in Aspen, which where to go looking answers for this, and also that's the whole idea of asking these kind of questions. Okay, just check what all the property methods available under the petrochemical property methods. Others? Hey, thanks for the responses. So I'll just show you how do we do. Go to properties. You'll be able to see the methods, right? Under specifications, just click on petrochemicals. Okay, so see the petrochemical. So you have so and so property methods, right? So now the question is, what happens if I use, let's say, the answer for this particular question is B and D, right? So what happens if I use PC shaft equation for this? So for simulation of petrochemicals, I will be use in one case I'll use PC shaft equation. Then what happens to that? What happens to my results? Or can I use PC shaft equation? The first question to be asked is, can I use PC shaft? In case if I'm using PC shaft, what about my results? Can you comment on that? Anyone? Not in base method of petrochem. Correct. I know this is observation. I'm asking you what do you infer. There's a difference between observation and inference, right? So this is observation. It's not there in base case of base method for petrochemicals. That's observation. So what do you infer from it? So can I use PC shaft for simulation of petrochemicals? What happens in case if I do that? Anyone else? Okay, can I use ideal gas equation for petrochemicals? Let's say let me be very specific. I have a mixture of methane, ethane, and propane. Okay, only three: propane, ethane, and methane. Only three gases. Okay, so in for simulation of any system having these three components, can I use ideal gas equation of state? So we can call methane, ethane, and propane as petrochemical products, right? First of all, do you agree with this? Can I call that? Can I say propane, ethane, and methane are petrochemical products? Okay. So now, can I use ideal gas equation of state for simulating a system which has got these three components? Uh, can you answer the question? So what happens if I use ideal gas equation for simulating a system which has got the mixture of methane, ethane, and propane? I'll discuss about assignment question. If you just give me some time. Towards the end of the lecture, we'll discuss. Okay, fine. Just think over it. We'll come back to that. What happens if I use PC shaft equation for petrochemical processes? On analogously asked you, what happens if I use ideal gas equation of state for modeling a system which has got ethane, methane, and propane? Okay, fine. Do you recognize this symbol in Aspen? Can you answer what is this symbol? What is the B2 block referred to as? Just open the flow sheet. See which one do you see this? Yes, it's flash to right, the separation model. Like, this is kind of a trivial question. It's a trivial question. So fine. By now, I hope you have Aspen in front of you. So in the last class we just started simulation of this air separation plant, if you remember. Can you just tell me how many of you were present in the last class of the 9 students today? How many of you were there in the last class? Okay, Sanjay, Sachin were there. Others? Yeah, Dhamaraj, you're correct. I remember reading your name in last class. Yes, that's all. Three of you are here. Okay, fine. Okay, so we just started simulation of separation plant. Okay, so we divided it into three regions as of now. First we'll simulate the liquefaction cycle and then the separation process. So basically we divided the entire process into three sections. Okay, so what we did in the last class is to just took simple feed. Okay, in place of air we started with nitrogen just for the sake of simplicity. We'll modify it to air. Okay, so we took nitrogen which has got feed at 100 kelvin, 40 bar, or what is the 5 bar, right? So then we said we'll send it through we'll send it to a turbine which has got isentropic efficiency of 70%, right? It is expanded to 1 bar. Then we have a phase separator where from the bottom we'll get liquid nitrogen and from the top we'll have nitrogen vapor, right? So Okay, since only two of you are here, we'll just try doing this once more. So, others, whoever have Aspen with you, other than these three students, who all have Aspen, other than Sachin, Sanjay, and Dharmaraj, who all have Aspen now? We'll discuss about the lectures, assignments. Okay. Yeah. So the last week we were stuck over here. Okay, we stopped the lecture in between. I asked you to find out the temperature, such the temperature of stream 5, such that you'll have the ratio of the liquid nitrogen produced to the nitrogen expanded is about 0.6, right? So that was the question which was asked. So Sanjay says it's changed from 6 to 83 at minus 178. So can you explain why do you think? So he is telling there is a just shift from 6% to 80% at one particular temperature. So that's what he observed. So can anyone explain why there is a shift of so? How many live sessions are where this is the seventh one. So after this you'll have five more. Okay, it's about 12 sessions in total. This is the seventh one. So after this you'll have five more. Why do you think there is a sudden jump? He says there is a sudden jump at a particular degree centigrade. Okay? From when he changes from minus 178 to minus 179, the fraction changes from 6% to 83%. Why does a sudden change? What do you think? See, Aspen will give you some results. It's up to you to decide whether the given results are correct or wrong. Inference is always important. So this is observation. There's a change of yield from 6% to 83%. When you change temperature or when you decrease the temperature by 1 degree centigrade. Now, what do you infer from it? That's more important than what you observe. Let me just open last week's file. See, with respect to lecture 24, I guess there is one more student who was telling there's some issue with the question or whatever. There is an explanation in the video. I'll have to go through it. Okay, I couldn't go through the lecture, so I'll come back to you. This is 24, right? I'll just take a note of it. I'll come back to you in the coming week. Okay. So what do you infer from it? See, I'll show you the result which I have. Do you see this? I wrote in terms of Kelvin and the flow rate. Okay. So when I increase the flow rate, when I increase the temperature, you see this? When I have it at 94 Kelvin, I have fraction of about 84.84, right? And when I increased it to 95, the value changed up to 0.06. So why do you think there is a sudden shift in the value? So I'll just make a statement. You tell me, is it true or false? A pure component boils over a range of temperatures. Is it true or false? A pure component means a single component boils over a range of temperatures at constant pressure. Is this statement true or false? False. Can you justify why do you say so? You can just unmute and justify. Okay. But I would claim it to be true. Can you justify? How are you telling it's a false? And can you give me an example where you have variable temperature boiling? You are telling pure component has got a constant temperature boiling rate. Then can you give me an example where you have variable temperature boiling? Others also can join this discussion. Okay, need not be only three of them. I can see those three students kind of, it's been really good number of weeks they have been active. However, others you rarely see. See, pure component boil at a constant temperature for the given pressure. Okay, so when you draw a PT diagram from Antoine's relation, what do you see? For a given temperature, you have a unique pressure, or for the given pressure, you have a unique temperature, right? What is Antoine's relation? It will give you the relation between pressure and the saturation temperature, right? Dharmaraj, are you talking or unexpectedly your mic got switched on? Can you just check?
I'm just trying to talk. I just This similar condition is when we plot the PT diagram, we got a boiling point curve.
Yes.
It's a single fluid mostly, and we set the operating pressure value for this specific fluid.
Correct. Yeah. So similarly, I'm telling this plot is from, as an example, you can say it's from Anton's equation. So what does Anton's relation say? For a given pressure, you have a unit temperature. So it's for the pure components. However, if you take mixtures, okay, say if mixtures boil over a range of temperature. You might have seen a TXY diagram, right? So depending on the composition, they'll boil over a wide range of temperature. Okay. So yeah. So since we have considered only nitrogen, which is pure component, it boils at one particular temperature. Right? So when there is a sudden change in temperature, you will be able to observe that there is a significant change in the liquefaction observed in the system. Okay? This is same case of the phase change and the expansion are the similar process. So when you expand, what happens in an expander is it's an isentropic expansion with which has got with some efficiency. We'll assume in this case we assume some 70% isentropic efficiency, right? So accordingly the outlet enthalpy is calculated. Okay. So because of this reason when you expand it from high pressure to low pressure, since it boils at a constant temperature, a sudden change in temperature, let's say from 94 to 95 Kelvin, you are able to observe a significant change in the liquefaction product which we got. Okay. So that's the reason. So in continuation to that, now so this is a simple liquefaction process, right? You see this, you have a compressor, you have just a cooler, after cooler, then there's a heat exchanger. Okay, after that heat exchanger, a part of it is expanded. Okay, a part of it is expanded and then added over here. Okay, and another part is further cooled and expanded in another turbine. The outlet of turbine is connected to a phase separator. The bottom product is called liquid nitrogen and the top product is added to the output of expander. The same stream is used to cool the incoming stream. Okay. So now I want you to set up only the cold box section of the process, which means HX1, HX2, expander, CD and the phase separator. Only these 5 components in your flow sheet. Okay, and further, so since we are operating at temperatures below 123 Kelvin, right? The air separation process happens at around 80 to 90 Kelvin. So since we are talking of temperatures below 120 degree Kelvin, it's called cryogenic operation. Okay, so any cryogenic operation, the process performance is evaluated in terms of exergy efficiency. So in this case, the exergy efficiency is given over here. Okay, it's just N7 into EX7 minus EX3 by N12 of EX3 minus EX12 minus of the the CT work and the expander work. Okay, so how is EXI defined? HI minus T ambient into SI. So HI is the enthalpy and SI is the entropy of that particular stream. Okay, and T ambient is 300 Kelvin in this case. So now I want you to set this cold box flow sheet in the Aspen which is available with you. Give the operating conditions which are given over here. Use the calculator block to calculate the efficiency and let me know the value. Can you do this simulation for me? Could you understand the question or shall I repeat it? Could you follow the question? One. Okay, no issues. See, now as of now I'm asking only to simulate the cold box section, the components which are included in this red box. Okay, so you have 5 components: a heat exchange, HX1, HX2, which are heat exchangers, and then an expander, and then CT, which is also an expander, and the phase separator. Okay, so now at condition 3 you have nitrogen, which is at 300 Kelvin and 40 bar pressure, which has got flow rate of 1 kilomole per second. Okay, it is cooled from 300 Kelvin to 225 Kelvin. Okay, and a fraction of it, which is about 37%, is sent for further cooling, and remaining 63% is expanded to 1 bar. Okay, it is expanded to 1 bar. Now the part which is taken away from the expander is further cooled to a temperatures of about 127 Kelvin. Okay, and then expanded in another turbine. Okay, which has got isentropic efficiency of 70%. It is expanded to 1 bar, right? Then you have a phase separator where the liquid and the vapor phase of nitrogen are getting separated. The separated vapors of nitrogen are used to cool the incoming high pressure nitrogen. Okay, so efficiency of such a process is estimated in terms of exergy efficiency. Okay, the definition of exergy efficiency is given over here. It's N7. It's basically useful effect by spent effect. Okay, this is the definition of exergy efficiency, and EXI is defined as HI minus T ambient into SI, right? So where HI is the enthalpy of that stream I, and SI is the entropy of that particular stream, and T amp is the ambient temperature. In this case we are assuming it to be 300 Kelvin. Okay, so using the data which is given in this slide, the entire data which are given in this slide, can you just do a simple simulation for me and tell me the exergy efficiency value? Only the cold box session. Okay, it has got 5 units: HX1, HX2, expander, CT, and the phase separator. Now could you follow the question? Everyone, could you follow the question? Sachin says okay. Sanjay, thank you. Others, could you follow? Will you be able to solve this question? Okay, can you do this simulation? I'll keep this slide. Just in between, give me your status. Okay, where are you up to, so that I can also do it parallel. Okay. So in case if you have any doubts, questions related to this particular question, you can either unmute and talk or just put it in chat box. Okay. whoever have Aspen with you now, please try to solve this question, and update me about your status. Okay, can someone tell me your status? Where are you? Who are all trying to simulate this? Sachin, Sanjay, Mantha, Dhamaraj, are you trying? Are you trying to simulate, or you are in office today?
No, I have the access for the software, but I don't have any available project. Means I have sent the PPT. Means in concurrent, I will send the PPT here. Or
Okay, see, as of now we are only doing for nitrogen. Okay, I just give you a simplified version. Don't take air. Consider air is only of nitrogen. Okay. Any other thing you are stuck with?
I am considering first I was joining like second year perimeter organisms or microbes.
Okay. Just try with nitrogen. Okay.
Yeah, yeah.
Yeah. I'll wait. Okay. Just let me know if you have any other question. I'll wait for some time and then start sharing the solution. I want you people to try. So if I keep on doing the simulation, this will also become like a regular class. So there won't be any specialty about the interactive session, right? So it will be good if you are able to solve it. Can you tell me your status? Where are you? Everyone, could you finish giving components? Can you answer, please? Yes, okay, thanks, Sanjay. What about others?
That's right. This formulation is just performed because we have two axes involved on the same line. So previous one we have dealt with single coordinate person that was in completely by direction. So if one is in x and one is in y, then formulate the residual value working better. If we need some more time, answer as well. So this is a neural pulse mechanical with two layers. So what are principal work in both layers?
Uh,
The sum of work done
what to use as expander?
by all the forces
For expander, use the compressor module available. Okay,
on a mechanical system
use
is
the compressor
equal
module.
for all
Change
those
it to
particular
turbine
forces.
instead of
So
compressor.
that's what we are going to write in
Flash
a
inlet
vector form for this
conditions. So flash
particular
inlet
part.
conditions
So
will automatically
WT,
be
that is
calculated by the
weight
CT
in
output.
both x
Okay,
and y
so you don't
direction,
have to
that is
specify
command
flash
that
input
will show you,
options. So
times
you mean
infinity
the
is showing
flash
the small
separator input by
vector
itself.
displacement, that
So
is
you can
delta
assume pressure
r.
drop to be
So
zero and the heat duty for the
that
flash is
location
zero.
is at this
These are
point,
the two. Excuse me. These are
and
the two inputs which you
Ft,
need to
that
give
is
for
the
flash.
reaction force
Okay.
which is exerted at this point into
Assume heat duty
displacement
to
at
be
this
zero and the
location
pressure
E.
drop in the flash separator to be zero.
The
Okay.
sum of work done by these two forces will come up to zero according to this formula. Or you
Any
can
other
see
questions do you have?
that term dr over dt problem.
So only
So
two
I'll
of you are
write
solving, is it?
the location of r. I'll take this
Of
point
the
as
eight?
r. So let me take this coordinate as 0, 1, 4.
What about
I have
others?
also stressed, and he has appreciated the fact that these taken zones are not coordinate dependent complexly. So the
Others are
choice
not
of
solving?
coordinate system or the axis will not change the answer. So you can take the choice of origin, the
See, just let me know in case if you are not solving, that's also fine. I need the data, what is the fraction of students solving, so that I can prepare question accordingly, okay?
times h, and what will be my delta r? It will be nothing but 0, because x coordinate won't change, that is a constant, so that will be 0. And what is h? H is nothing but 2l sine theta. So once I differentiate that expression, I will be ending up with 2l cos theta times delta theta. Okay. H is nothing but 2l times of sine theta. Okay. Because this link length is L. So this half length is nothing but L sine theta. So the next half is L sine theta. So combined H becomes 2L sine theta. So once we take a derivative of that, it is 2L cos theta times delta theta. Okay. Now we have one displacement, that is delta RR, that is complete. Now we are left with finding out delta RA, that is the displacement, infinitesimal displacement at this location P. So we write RA as s comma 0, because the y coordinate of this point is 0. That can be seen. So s, what is s? S is nothing but L times cos theta. So once I take a derivative of that, that becomes minus L sin theta delta theta. Okay, I think that is clear. S is nothing but L times of cos theta. That is a simple thing to observe, because this is L.
Expander needs
So
one more
length is L.
specification. What more do you need, Sachin? See,
So
we
integration
know
S
the
becomes L times cos
we
theta.
know the
So
inlet
once we take a
conditions
derivative of this
because it's
S,
already given.
that is nothing but minus
Temperature,
L
pressure,
sin
and the
theta
flow
delta
rate is
theta,
all known.
and y coordinate
And
is
you know the
that
outlet pressure, which is 1 bar.
So W, which is
You
acting
also
in
know
the
the isentropic
vertically downward
efficiency as
direction I,
85%.
represented as
What
0
more information do you
comma
need for
minus W
expander?
theta. And the reaction force, that is F, I'll write it in a matrix form as Fx and 0, because it can only give reaction force in
Yeah,
Fx
that's all.
direction, x direction, that's what is mentioned. So y component of this force is 0. So I go back and substitute this vector formulation in the principle of virtual work, W into delta R plus F times delta R is equal to 0. So we have all the expressions in vector form now. So these will be in terms of 4 matrices, 0, minus WT. Yeah, sorry. Yeah. Fx. Why can't we take 2L cos theta? No. The link length from here to here is L. Okay. Now this angle is theta. Now we take a projection of this link length onto the x-axis. That becomes L cos theta. So this distance is only L cos theta. Okay. Yeah. Why did we end up with 2L sin theta for Hs? This is link length L and this is theta. So this half distance is nothing but L sin theta. This distance is L sin theta. So the upper distance is also L sin theta. So combined becomes 2L sin theta. Okay. So once we get all the formulation in terms of matrices, we just have to plug in the values, that is 0 and minus WT times RA, that is 0 and 12 cos theta theta, plus Fx 0 into minus L sin theta delta theta comma 0. That equals 0. So Fx comes out to be, once we simplify this expression, Fx comes out to be minus 2 times Wt by tan theta. Now we have one more problem to find out, challenge to find out. find out tan theta, we again go back to this triangle. We call it OAX. Now, to find out tan theta, this is nothing
You
but
need to
h by 2
mix expander outlet
by
and
L.
flash. Yes,
That's what is tan
you need
theta
to mix
1 by
both of
L.
them.
So,
Do you see the stream 9
or
and the
I'll
stream 8 are getting
write my
mixed to
sin theta
become
as
stream
1 by
10?
2 by
Okay,
L.
you need to mix both of
So
them. Okay.
from here I find out given h and L, I'll find out the theta as 35.68 and plug this value of theta into tan theta equation. Now once I plug the value of theta into this expression of fx, I end up with minus 557.46. So this minus indicates that the direction of the force was wrongly assumed. I assumed in the positive x direction, but the solution tells that it is in negative x direction. So this much amount of reaction force is applied at pinch A in the negative x direction. Any questions for this? Okay, there are no further questions. I'll show you one question related to axial friction analysis. This is an extension of the problem of velocity analysis which we have taken in the last class. We had a collar joint or a pneumatic joint, which was like which we had to know the velocity of that velocity at point C. So for this problem, we want to know the acceleration of link AC for the given kinematic change at theta 30 degrees when theta dot, that is angular velocity of link OA is 2 radians per second and the acceleration of link OA being 0.1 radians per second square in form
So Sanjay and Sachin, can you tell me your status? Where are you?
I'll give you a few minutes of time. This is not much different from velocity analysis. In fact, we just have to
Completed.
take one
You
more
finished the
calculated block.
simulation and the exergy calculation also.
I'll give you about a couple of minutes.
So Sanjay, could you? No, sir, only simulation. Okay, can you set up the calculator block as well and calculate the efficiency? What about Sachin? Where are you?
Sorry. I'll give a minute or so. How many parts? I'll give a minute.
Sachin, can you respond?
In our syllabus, we don't have practical solutions. We are proceeding with the analytical. Graphical solutions are also there.
Just last slides. Okay. Okay, fine. Sanjay, just let me know once you're done with the calculator block. Okay.
start applying the cosine rule in this triangle OAC. So L squared equals the length are already given 80 squared plus 240 squared times 80 to 40 into half 30 degrees. So the length comes out to be 175.34 mm. So or the analytically I can write it as L squared equals OA squared plus OC squared into AO OC cos theta. Now I take a time derivative of this expression A. So I'll end up with 2 times L into dl by dt. These two terms end up to 0 because they are constant in length. So I'll be ending up with minus 2 times OA OC minus sin theta into d theta by dt. I take one more time derivative of equation 1 and I get equation 2. So L times the acceleration component that we were looking for plus L dot squared equals OA OC cos theta d theta by dt, and again we'll go back to the same rule OA OC d square theta by dt square into sin theta. Now from this expression from equation 1 we can directly find out the value of L dot as 109.50 mm per second. So that's the linear velocity of the L orbiting AC. So the other expression, that is L double dot, is to be found out from equation 2 that
Okay, Sanjay, what's your status? Could you finish the calculator block?
L dot is
Okay. See, exergy efficiency is defined as the useful effect by the given input. Okay. So it's just the mole flow of steam 7 multiplied by the exergy difference between the steam 7 and steam 3. Stream 7, which you have liquid nitrogen, and the stream 3, which is the input. Okay, that's the useful effect. And what is the given? It's mass per mole flow of steam 12 multiplied by exergy of 3 minus exergy of 12, and you subtract the work of the both expanders from this. Okay, how is EXI defined? It's HI minus T ambient into SI. HI is the enthalpy of stream I and SI is the entropy of stream I. Okay, and Tm is 300 Kelvin. Okay, so this is how the formula is defined. Could you get it?
d theta by dt is already given, that is theta dot, that is given in the question. Theta is given as 30 degrees, sin theta can be done.
Could you get it, Sanjay?
OA and OC are already given, that is OC is 240 and OA is 80. So
oh, steam I means I refers to the values 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13.
From here.
I is just the value. Okay, it can be any steam. That's this is a generalized way of writing.
So once we get L dot, we have to substitute in equation 2. We'll be using the analytical solution only in our course. And graphical solution are also there. Any questions here? There are no other questions. We will conclude this session with one small question. This we have already known. The given state is theta 4 dot, that is in the 4 bar mechanism, 4 are changed.
Okay, fine. Now let me just show you the procedure. Just waited almost 20 minutes. So the first step is to give the components, right? In this case we are only using nitrogen, so we give nitrogen, and then methods we just specify Peng Robinson. Okay, then we'll go to simulation. Okay, sorry, I'm using the old file. I'll use it and use it another one. Okay, so first step is to specify the components, then we specify methods, right? Then you go to simulation. So we have seen that we require in total 5 units, 2 heat exchangers, 2 expanders, and 1 phase separator. Let me just place them. Okay. I have two heat exchangers. Correct. Then I have two
Sir,
expander.
we can't see your simulation on the screen, sir.
You can't see my screen?
It's only the problem is coming.
Is it? Okay. Let me do it again. Share the entire screen.
Okay. I leave this small task as an assignment for you to answer.
Do you see this now?
Next discussion. Maybe I'll start with this.
Can you just confirm that you are able to see?
Yes.
Okay, great.
Yes, yes, I have
Okay, so I have put two heat exchangers, then we need two expanders, right? So I have two expanders,
There are any questions
then I have a
regarding
phase
this class,
separator,
you can ask me.
right? Then I need a splitter between these two, then I need a mixer after this, right? So that's all unit operations we require. Let me just rename so that we don't have any confusion. So after this we have a splitter, turbine. This is splitter, this is expander, and again we have HX2.
For
Let me just flip it.
no, for
So this is mixer,
for finding
and
out
then this is named as turbine, and then we have phase separator, right? So now I have nitrogen which is coming at 300 Kelvin. The hot is it's cooled to about 225 Kelvin if I remember correctly, and then sent to the split, right? So one is sent through the expander and another portion is sent through a heat exchanger, and the one which we obtained in the expander is added through this mixer, right? The one which is going out of heat exchanger is connected to CT, and from CT it is connected to phase separator. Phase separator, one is liquid product and the vapor product is taken to the mixer, and the mixer outlet is connected to HX2. From HX2 outlet it's there to HX1, and HX1 outlet is turned to space, right? Let me also give the same stream names. So this is stream 3, 4, right? The one which is going to heat exchanger is 4B. This is 4A, and then expander outlet is 9. HX2 outlet is 5 and followed by 6.
1:1 or 2:1, whatever you feel
Right.
appropriate on
This is 7 and 8.
Then start with displacement analysis of each link. Once you find out displacement
7, 8,
analysis,
and
you
then
go with velocity
this
analysis. So
10,
these velocities are proportional to the
11 and
distances
12.
that you get on a graphical sheet. So from that you go ahead and
Fine.
solve for
Okay. Now the first step is to give the basic input for this. So given it's 300 Kelvin,
then you can perform force
40
analysis
bar,
on those diagrams.
then 1 kilomole
So
per
it is not like
second.
we can directly
Okay, it's only nitrogen, so I'll take mole fraction to be 1. Then next, this is cryo turbine, right? Discharge is 1. We assumed isentropic efficiency of CT to be 70%. Since there is a possibility of two phase, I'll also give it's vapor and liquid. Okay, and then next, this is another turbine. Isentropic discharge pressure 1. That's 85%. Then next, this is HX1. So we know the hot outlet temperature. This is HX1 225 Kelvin. Okay, since there's a possibility of change of significantly, so I'm doing it as an internal analysis, and then I click on next, and then hold, and then temperature. This is about 127 Kelvin. Right, let me
Then
also
one
give
has just
here,
asked for the NVIDIA team
and then
whether we
this
will
is
be having
flash.
the live session on 28th or not. Okay.
Okay, and then next, this is we have about a 37% going to
No, the
4B.
exam date will
So
be
that's all
as
right.
per the NVIDIA
It
schedule.
says the
There
given
is
input
no
is complete.
changes, right?
Let's run this
Okay.
simulation. Let's see if we have get
Whether
any errors.
the live
We
session
may
that
get
we are handling
because
since
the
last
values which I
7
gave
days,
are
that will be
not
there in
from
the next
reference.
Tuesday or not.
It's
I
just
will confirm
from
it
my
in the
memory.
NVIDIA team.
So it says some error with the
You
expander.
can
Let us
mail the
see.
NVIDIA team. I do not handle this. It has already come.
A liquid
Okay.
exists. Okay, so what we'll do is
So
we'll change
the
this one to
exam,
vapor
I am
liquid.
stressing that the exam will be as per the NVIDIA schedule. There will be no change with respect to that. Whether we have a
Okay, now
live
now
session
results are
again on
available.
28th
So
or not, I will just
the
confirm
simulation,
in
is it
the
clear for all
NVIDIA
of
team,
you?
and
How did I simulate?
accordingly we'll have a class at 6 o'clock. If
So inlet to the phase separator, what we did, we said that the pressure drop to be 0 and the heat duty to be 0. Okay, these are the two specifications we specified for the phase separator.
yeah, 5th and 6th I have already uploaded. The 7th,
So with respect to simulation,
7th I'll be
could you
uploading
follow?
it by tonight.
Whatever I have shown you on the screen. Okay, great. So let me just show you the calculator block as well. What are we supposed to do? Now since the simulation is converged, now go to the flow sheeting options calculator. Okay, so just rename it as whatever name you want to give. Now first of all we need to define what all the inputs we need. So we need N7, which is flow rate 7. Since we need to calculate EX7, so we need H7, HS7, right, H3, S3, and then N12, H12, S12, WCT, WEX, WEX, and then what do we have? It's the efficiency, right? Let's see. That's all. So let me just call this as the import variables. Whatever you are importing from the simulation, we call it as import variables. Okay. Whatever we want to export, we call it as export variable. Okay, so individually we need to define. So since this one we defined as export variable, we'll go to model utility, then parameter, let me call it as 1, first parameter, and then N7. Since first one is the flow rate, so we'll say it's a stream value. What is it? Of the stream 7. What is it? It's flow rate, right? And then it's stream 7. What is it? It's a stream property, right? Enthalpy is a property. Which stream? Stream 7. Then we'll say it's molar enthalpy. And similarly, we'll go to entropy, stream value. It's a stream variable, stream 7. It's entropy, right? Just check the units, okay? Be consistent with the units. Let me just check. For enthalpy, it's calorie per mole. Let me change it to what was the flow rate? Okay, let me put it in terms of kilomole per second. In terms of enthalpy, it's kilomole per second, right? So I'll write joule per kilomole. Okay. For entropy, joule per kilomole Kelvin. Okay, so be consistent with the units, or else you'll have some errors. So this is enthalpy of stream 3. Enthalpy more from the joule per kilomole. Similarly, entropy the third one, entropy, joule per kilomole. String 12. Kilomole per second. So this is a block variable, right? CD is the network. It should be in watt because we are using in terms of joule per second, right? So we'll put it in terms of watt. And similarly for WEX as well. This is a block variable. Which block? It's an expander, and then what is it? It's a network. And then put it in terms of watt. So now we'll define. We'll say Tm is 300 Kelvin. Okay. X3 is H3 minus Tm into S3, right? Then EX7 is H7 minus Tm into S7, right? Then EX12 we have it as H12 minus Tm into S12, right? And then you have useful effect as N7 into EX, am I right? And 7 into EX7 minus EX3, and what is spent? It's N12 into EX3 minus 12, X3 minus 12 plus EX. See, make sure that you have a minus over here, because a minus means the overall value should be minus. In the simulation what I have seen is the work is calculated to be negative value, okay, since we are expanding. So in the calculator block accordingly you are expected to give. So I gave plus W, okay. Then I will calculate EXEF, which is our required thing, which is what we defined as our output right here. Where is this? See, the export variable EXEF. Then we'll define this as useful by spent. That's all. So once this is ready, just reset your simulation, save your file, then run it. There we have the result. The value says about 40%. Okay. So this is how you calculate or use the calculator block in our simulation. So one example I have shown you is how do we calculate the efficiency of the liquefaction process. So which is what is shown over here. So could you follow how did I do this? So what you can do is in the expand, just go to the expander thing. Go to expander. In case if you have the warning of two-phase entry, just change the go to convergence tab. In place of vapor only, click on vapor come liquid. So that will help you to take out this warning. Could you follow whatever I have shown? Okay, thank you. So do you have any other questions? Fine, it's not a big issue. Okay? It's just a warning, it's not an error. You don't have to worry about it. Okay, let me just take note of it. See, I didn't see your assignment date. Okay, I'll just check it and come back to it. This week, assignment date. Okay. Any other question? What is issue with part B? It shows material balance is wrong. Okay, fine. I'll just check with Sachin. See, with respect to lectures, if you have any specific questions, you can just point out. Okay. Then in the coming lectures, I can pick up that particular topic and then discuss. Okay. Which lecture you want me to discuss in specific? If you can tell me that point, I'll discuss it in separate. Lecture 24 methanol synthesis. Fine. So if you can just tell me specifically that you need something of this, then we'll discuss. Okay. So methanol synthesis. I'll just take a note of it. I'll try coming next. Yeah, Lavraj.
I have got regarding RCS test.
Okay. I have to check it, Lavraj. I didn't see what is lecture 24. So it's difficult to remember each and every lecture, right?
Lessons, but it's showing error.
Okay, fine. I'll check it. I'll check it and come back to you. Okay.
I will show it.
No, see, I don't even know that. But anyway, you can share. I'll stop presenting. Okay. You can just share your screen. But I don't know the question. Okay, at this point of time, so it will be difficult for me to answer. You can share your screen. Yes.
Sir, I will open the camera.
Okay, you want to open your phone camera? Okay, fine. I'll pin you. Yeah, it's on now. Just flip the camera. Can you read the error? I can't read. No, I am unable to read. Can just read it for me? I can see that there is some error, but I am unable to read.
Error in the reactions paragraph. First ID R1, second ID general, reaction number 3 in reaction 1 has a solid component solid substrate. For equilibrium reaction, solid component is only allowed in mixed substrate.
Can you read it one more time?
Error in a reactions paragraph. First ID R1. Sir, it is regarding about RCSTS.
Okay. So essentially, you are entering into solid phase. Is that what it means?
But I enter only PV.
Okay. See. No, it's not clear. Okay, Ravaraj will do one thing. I'll try to solve it and come back. Okay, you just put your email ID in the chat box. See, if you have got assignment date, submission date tomorrow, in that case, we'll discuss about the solutions in the coming week. Okay, I'm not supposed to discuss about assignments prior to the submission date. In case if there is some serious issue with the question itself, I can notify to the relevant person. However, before assignment deadline, I am not supposed to discuss about it. Okay. Fine. I have your mail ID. I'll share, or I'll try solving it and discuss with you over email. Okay. Any other questions?
Sir, it is not regarding assignment, but I made it. It is in my project.
Fine. I'll try doing it, Laura. You just told me, right? You.
Sir, can you please share your email ID?
Yeah, I'll put it. Just put it in the chat box. That's my mail ID. Okay.
Thanks.
Yeah. So, any other questions you have?
No, sir.
So Lavraj, you are from Anit's college, is it?
Yes, sir.
Okay, Vishakhapatnam.
Yes, sir.
Okay, okay, fine. You are a student there, or
Yes, sir. I am final student.
okay, fine. Okay. Any other questions do you have?
No, sir.
Others? So in that case, can we come back next week? Fine. See, if there is a serious issue with respect to question itself, I'll surely notify. Okay, I'll notify now itself, just immediately after the class. Okay. See, I'm not the one who is preparing your assignments. Okay, I can just convey to the person, whoever preparing the question. So in case if everyone has the same issue, that means there is some problem with the question itself, possibly. Okay. So I'll convey to the person, whoever is the in charge. So any other questions if you have, we can discuss. So if you don't have any other questions, can you come back next week?
Sir, regarding the assignment, I am not asking directly the same question, but the problem is regarding the PFR having the multiple Q conversion. So at least just take general, by taking general example, can you describe the how to set that reaction kinetics for this set of reaction, type of reaction?
See, I'll tell you something. Before deadline, I was told not to discuss anything related to that. Okay. So after deadline, I can discuss. I can show you the solution also. But according to the instructions which are giving to me, I'm not supposed to discuss anything relevant to the assignment directly or indirectly. Okay. And with respect to bonus marks, it's out of my jurisdiction. I can't even give a word about it. I'm just a tutor where I'll come every week and discuss about your doubts. Okay.
Okay, sir.
Yeah. Fine. So in that case, we'll see you next week. Okay. Have a good week.